Let's take a look at how the stereochemical and regiochemical considerations mentioned in the previous video apply to reactions. And then we can start to develop a common pattern in addition. So here we're going to do a hydrohalogenation. And once again, we should always be asking ourselves, what is going to happen? Who are our main players? Well, with addition, we're going to have the double bond act as a nucleophile. And here it's going to come in and grab the hydrogen. Since the double bond grabbed the hydrogen, we're going to form a carbocation at the secondary position, which should make sense since we want to form a carbocation where it has more neighboring carbons, a more stabilized carbocation. But something to notice here is that since we formed a carbocation, we should ask ourselves if rearrangement could happen. And it can, because we can get a hydride shift from this carbon to the left over here. Now, that's going to give us two different products, one that rearranged and one that didn't. So if I have the Br attack before the rearrangement, as in here, then we'll get this, addition. And keep in mind it is Markovnikov addition because it added to the more substituted spot. It added the secondary carbon instead of the primary carbon. But we must consider, as I mentioned before, what the product looks like after the rearrangement. Well, this is going to put a carbocation right here. Well, we'll get the same attack we did with the bromine atom that was left from the starting material. That will come in and attack just to do the addition. And what we'll get is we'll get this. In this example, we see that a lot of addition reactions actually create a carbocation as an intermediate. And because they create a carbocation, we have to consider if rearrangement can occur, as happened here, and then resulted in a more substituted carbocation. Speaking of a more generalized reaction mechanism for addition, we see that it's common for the double bond to come in and attack the hydrogen, then having a resulting carbocation that is attacked by a nucleophile. Of course, we'll see some variations on this, but let's move on to the next example. In this example, we're going to see a very similar reaction to what we saw in the previous slide with hydrohalogenation, but in this time we're going to be doing a hydration, essentially adding a water molecule across the double bond. So looking here, considering that we're in acidic conditions, I'll want to go ahead and draw my proton vehicle, as I like to call it. So it's going to be the hydronium ion, most likely since we have acid as a catalyst, which means that this is acid-catalyzed hydration. So again, the first step in this addition reaction is going to be the attack of the nucleophilic attack of the double bond to abstract a proton. So it acts as a base in that sense. When we draw the result, we're going to put a carbocation on one of the ends of where the double bond was previously. So I can draw, let's say, the added hydrogen right here. Now keep in mind, there's no difference in the substitution of both spots where the double bond was located. So it is, we would see anti-Markovnikov addition, but in here there's no need to rearrange, there's no real preference, and there's no difference. It's a symmetrical molecule too. Well, going back to the reaction, so we've created a carbocation, we should expect something to come in and attack. Well here, the thing we have to consider what can act as a nucleophile, and here that's going to be water. Water has lone pairs. Water can form a bond with one of its lone pairs. And this is acidic conditions, so we're used to seeing positive charges being formed. So if I draw the electrons in, that will come in and attack. Well, of course, you should realize that while it does add the water molecule, we're still left with a positive charge on the oxygen. Well, this is acid-catalyzed conditions, so we know that our catalyst, or the acid, the proton, is going to be reformed. So in this case, well, after we had the hydronium ion leave its proton, or donate its proton, we can have a water molecule come in and abstract the proton off of the added water to the molecule. So once again, if I draw those electrons in, those would come in, abstract a proton, these electrons would fall down, just a simple proton transfer, and that would leave us with this. So, and if I draw the other hydrogen we added across the double bond, we see that we've added a water molecule across a double bond, and thus it's a hydration. So keep in mind here, we had no real stereochemistry because once we create the double bond, it's flat, and then we can come in from either side, so over here, or on top, or on bottom, per se. So we're not going to get any sort of syn addition or anti-addition, as we'll see in some other reactions later on.